Many major quantum gravity programs, like causal sets, dynamical triangulations, and tensor networks, aim to recover macroscopic continuum geometry from discrete microscopic primitives. These models often assume coupled spacetime, or an absolute time coordinate. The boundary condition quantum mechanics framework, specifically BCQM VI, abandons these starting points. It begins entirely pre-geometric, with no manifold, background geometry, or predefined time coordinate. The model operates under a strict constraint. Both time and space must emerge independently as measurable order parameters, driven by the mechanics of a discrete event graph. If space and time are distinct properties derived from lower-level rules, they must be mechanically separable at the pre-geometric level. Testing that separation directly challenges the assumption that spacetime is indivisible. The core thesis of the BCQM VI paper establishes that spatial connectivity and temporal coherence are driven by completely orthogonal mechanisms. By systematically disabling parts of the simulation, researchers discovered a clear mechanical separation. A spatial substrate can fully percolate and exist as a connected web without a functioning operational clock. The data also reveals how macroscopic classicality behaves early in the emergence process. When spacetime begins to form, it fails to stabilize uniformly. Early spacetime manifests as dynamically fluctuating islands of coherence. These temporary pockets of localized spacetime are highly sensitive to overlap thresholds, appearing and dissolving rapidly. This two-step emergence, where a stable spatial web forms first, followed much later by localized islands of spacetime, revises how physicists look for the onset of classical geometry in quantum graphs. The BCQM simulation starts with a primitive ontology, featureless events, and directed connections. It constructs threads advancing via newly realized events. This baseline, labeled no space, features parallel thread histories with zero cross-communication and absolutely no shared spatial events. The first distinct mechanism layered onto this primitive graph is the BCQM VV-glue engine. The V-glue engine functions as a temporal coherence module. It couples the phase and cadence of these independent threads, manufacturing an operational time direction. This produces our first measurable order parameter, Q clock. This metric quantifies the temporal coherence and overall clock quality of the threads. In this baseline state, the system successfully generates a functional operational clock, where Q clock approaches a value of 1. However, the system contains 0 spatial dimensions and 0 spatial connections. Spatial connectivity requires the introduction of the second major mechanism in the scaffold, a parameter called Path A. Path A introduces a precise operational rule. When a thread advances, it does not always create a new event. Instead, it has a set probability to reuse an existing event from a defined active time window, denoted as V active. This reuse probability is governed by a scan parameter known as crosslink pressure, represented by the variable n. Reusing events generates junctions across the graph. This transverse linkage is the operational definition of space. We track this spatial connectivity using the percolation fraction, or S-perc. It measures the percentage of the active window captured within the largest connected component. The researchers tested the system by slowly dialing up the crosslink pressure. At low pressures, between an n value of 0.2 and 0.4, spatial connectivity rises sharply from 0. The temporal structure behaves differently. While space connects rapidly at low pressure, the formation of coherent spacetime islands, measured as Fmax, remains fragmented until the pressure is dialed much higher. Generating a connected spatial substrate takes minimal crosslink pressure. Binding those events into a unified spacetime geometry requires significantly higher overlap thresholds. To verify that space and time are independent here, we must rule out a mechanical dependency. We need to check if the spatial crosslink parameter is leaking into the temporal clock engine and driving it. The researchers designed the glue-off ablation condition. This targeted test is built to disable the operational clock while leaving the spatial crosslink rules active. To implement glue-off, the simulation disables cadence couplings, forcing temporal coherence to collapse. The data shows clock quality dropping to 0 while spatial percolation remains high. This perfectly inverts the no-space baseline, where perfect clock coherence existed alongside 0 spatial percolation. The ablation tests demonstrate that spatial percolation functions independently of the clock. Space and time operate as modular, separable subsystems within this pre-geometric scaffold. When both mechanisms run simultaneously at an intermediate crosslink pressure of 0.4, the resulting spacetime exhibits intense dynamic variance. A time series diagnostic tracks this variance continuously. The line for spatial percolation draws horizontally, remaining completely stable. Directly below it, spacetime coherence fluctuates wildly. The interquartile range shows massive statistical variance as these coherent pockets of spacetime rapidly appear and dissolve. This intermittent behavior aligns with physicist W. H. Zurich's work on decoherence and the emergence of classicity, where stable structures only form in isolated, threshold-sensitive regions. Macroscopic spacetime does not switch on as a unified block. A fully connected spatial graph persists as a stable physical reality long before temporal coherence solidify into localized classical spacetime regions. Analyzing this highly fluctuating active slice creates a methodological challenge. Measuring geometry usually assumes a continuum manifold. Applying that assumption here distorts the data. In this scatter plot mapping a return probability spectral dimension set, the pre-geometric random walk data hits a chaotic, flat plateau, causing the mathematical fit to fail completely. The failure is structural. The active slice is finite and rapidly mixing, meaning random walks scatter across the graph too quickly to establish stable curves. Without a stable power law regime, the resulting fitted dimension is mathematically ill-defined for the object being measured. To accurately map the active slice, BCQM VI relies on a robust network-theoretic alternative, the ball growth fraction diagnostic. Ball growth measures geometry by calculating the fraction of the largest connected network component that can be reached within a specific discrete graph radius. When measuring raw pre-spacetime, imposing continuous manifold scaling hides the actual topology. Intrinsic discrete graph diagnostics provide the only clear picture of the structure. Comparing ball growth ensembles, a crosslink pressure of 0.4 creates a slow, shallow curve. Pushing pressure to 0.8 forms a steep, rapidly rising curve. The effective diameter shrinks, hitting 50 and 90% coverage at a fraction of the original radius. This tightening effect reveals a topology of channels and shortcuts. The emergent graph is locally sparse, but possesses dense, high-speed interconnections across its global structure. These Stage 1 findings operate within a strict empirical limit. The active slice being measured remains short and localized in the present time window. In the paper's terminology, this localized structure is simply a short yarn segment. It is an isolated piece of a much larger evolving graph structure. The objective for Stage 2 research is to transition away from this localized yarn and define a persistent cloth. That requires finding an epoch-spanning union graph stable enough to support genuine metric scaling. BCQM VI demonstrates that space and time can be bootstrapped independently from discrete events. That separation moves physics one step closer to isolating the exact mechanics that weave the quantum void into a stable universe.